Hey, Year 12. Thanks for coming along. Got 4 people waiting. I have noticed that nobody, not a single person, has filled in their data for papers 1 and 2. Like, everyone should have seen the webinar that I did yesterday, and you should all be filling in your percentages. I do need your help, folks. I do need you to input your data for this. Obviously, we start school on Monday, so we'll still kind of trying to decide the content for Monday. I don't think I'm starting the A2 content. I'm going to be doing probably a couple of paper reviews for AS, I think. But we will be starting A2 content soon. Right, so I'm going to crack on with the paper. So let's do share screen. Hide, and then that one. Right. So, Donna Tenzi, thanks so much for coming. If nobody else shows up, I know I've got 4 people watching. Not in. Oh, hi Ria, thanks for coming. So this is the paper that you guys should have done. Ben sent me a message on the chat. Just saying that he no longer had access to paper 3. I thought I'd let you know where I got these from. These are just from Save My Exams, and they're just there as the Edexcel International A-level papers. They're all available. You don't have to be logged in. You don't have to pay for anything. They're just available. So you can just grab any of the papers, paper 2, mark scheme, paper 3, etc. So if you're wanting to know where they are, they're there. Okay, so we're going to start off with a multiple choice. Now, I need a favor. Ria, are you there? Is Ria there? Oh, hey, Kayan, thanks for coming. I need somebody just to kind of just be checking on me in case I make a mistake on any of them. Multiple choice are hard, and I never expect to get them all right. So I guess what we'll do is, I'm tempted to run the paper, run them up. What we're going to do is we'll do the multiple choice, and then we'll tally up the score and see how many I get right out of 20. I think that's a good shout. Okay, so in fact, Ria, you don't really need to do anything. I'll tally them up as we go along. Okay, so multiple choice. The diagram shows the trend in first ionization energies of group 2 elements. Ooh, okay. So group 2 elements, beryllium, magnesium, calcium, strontium, SR, barium. I think that's right. So we know that the atoms are getting larger as we gain a shell. So we know that the ionization energy is going to be really hard for the first one and really easy for the last one. So the answer here for this one is either going to be A or B. Now, to get a linear progression is kind of unusual in ionization energies, up, down, left, right, and in reality, you never really get a true linear fashion decrease like that. There's usually bumps and kinks. If that wasn't quite so straight, I'd half have guessed that one, but I'm going to go for B. So there's another reason for this as well, because the reason why strontium and barium, you notice that these guys drop very quickly and then it kind of levels off a little bit. The reason why that is because we've entered into, we're picking up with strontium and barium, we've got the D block electrons. So the electrons become a whole lot more messy, and it tends to not get substantially easier as you then move down the group. It's far more linear when it comes to group 1. Group 1 is almost linear, but group 2, not so much. So I'm going to go for B. It's going to be my answer on that one. Next, okay, write the equation for the reaction with calcium with water. Now, just to say, by the way, with water, that's important. Group 2 with water. So we're going to form the hydroxide of it, and we're going to form hydrogen gas, of course, as a byproduct. So we just need to make sure we've balanced it correctly. And I think it's going to be C. Yeah, that looks right. 1 calcium, 4 hydrogens, 2 oxygens, 2 oxygens. Cool. So it's going to be C. Now, if it had been with steam, then it would have been A. Calcium and magnesium do the same thing with steam, which is they don't form the hydroxide, they form their oxide instead. This is because their hydroxides go through thermal decomposition to form the oxide and hydrogen. Okay. Next. Okay. Barium carbonate is more stable to heat than magnesium carbonate. Okay. Stability of carbonates. So we've got magnesium 2+ and the big fat carbonate ion, which looks like this. CO3 2-. So it looks like that. It would actually be more directed if you wanted to actually draw it correctly. Actually, can I just point out, by the way, this is actually still a little bit of a fib, but it doesn't really matter. Just pointing the negatives over towards the MG. And what's going to happen is this is going to become distorted because of the small charge, whereas barium carbonate is massive, Ba2+, and it's a similar size to the carbonate ion, so less distortion. So this one is more stable. And it says, which ion causes the greater polarity? So it's magnesium because it has a higher charge to size. Right? It's very high charge density is the key term. So the answer is either C or D. And then it says, which bonds are weakened? Right, so the bonds that are weakened are the bonds that are inside the carbonate ion. Yeah, these bonds here are the ones that are actually affected. It stretches and pulls them, so it weakens them. So my answer then, therefore, is going to be D. See, the CO in the anion makes much more sense. Group 2 compounds give different flame colors. The best explanation for this. Gaps between the electron level, that's going to be my answer. But ionic radii, nope, makes no difference. Number of electrons, no. Although it's technically possible, if you've got a different number of electrons, then you'd have a different gap. But do they have different electrons? It's got a different shell. Oh, that's the first one I'm really questioning. Yeah, first, second ionization, yeah, it makes no difference. So A, I'm going to go for A, but I'm definitely going to flag that one as, yeah, I think I'm right. It is the energy gaps that make a difference in the colors. So I'm actually going to say I wouldn't change it, by the way. But okay, next one. 25 centimeters cubed solution of sodium carbonate contains 2.12 grams of solute. What is the concentration? Okay, first of all, flip to moles. Number of moles is grams over rams. So what's the MR of that guy? Sodium is 23.1. Eek, hang on. A-level table. 23.0. 23.0 times 2 plus 12.0 times 1 plus 16.0 times 3. Add those together, what do I get? 23 plus 20, calculate my return. Well, 23 plus 23 plus 12 plus 16 plus 16 plus 16. And I get an answer of 106.0 at A level, don't forget. Grams over rams, 2.12 divided by answer gives me 0.2 moles. 0.02 moles. Next, we're going to put this in 25 centimeters cubed. Number of moles is C times V over 1,000. Why over 1,000? Because we're in centimeters cubed. We're looking for concentration reorganized. Times by 1,000, divide by the volume. And that'll give us C. So times the moles by 1,000. So times by 1,000, divide by a volume of 25. And I get an answer of 0.8. We're done. Titration was used to find the volume of hydrochloric acid needed to neutralize sodium hydroxide. Well, that's nice. It's a 1-to-1. It's always nice that they didn't give us an equation. That's quite mean of them. Yeah, but luckily we're all capable chemists in this room, and we all know that it's a 1-to-1-to-1-to-1. This is good. So it then says, oh, percentage errors. It says the burette is 19.4. Each reading. So that one needs to be doubled because you take a start reading and a final reading for a burette. So that's times by 2. The pipette is times by 1. So percentage error is plus or minus value divided by 19.4. Yeah, plus or minus value over the volume taken. And then you double it. 0.05 over 19.4 And yeah, times by 2, shift eng. It's a tiny amount. Total percentage error. Let's just make it easy for ourselves. Let's just double that. 0.1. Do I need to do 0.1 over 19.4 times 100? It's easy to miss, isn't it? Times 100, that gives us 0. So this one gives us 0.52%. 0.52%. Oh, right. So it's either C or D on the burette. And then the total is, for the pipette, is 0.06 over 25 times 100. 0.06 divided by 25, all times by 100, and I get 0.24. So I've got C. Done. Moving on. Oh, kind of dumb question, but why isn't the pipette times 2? Good question, Ria. That's definitely not a stupid question. The reason being is when you have a burette, when we've got our burette, we know that we fill the burette, we've got these lines running down the sides, and we fill the burette to a line, and we take one reading for the initial volume. Yeah, we take initial volume, and that is usually, especially, it really upsets me that students do that, but I hate it. You should never take a 0, reading for initial, because chances are you're wrong, you see. But if we took like that, and then when we drain it through, we take a second reading at the end, an end reading of, let's say, 19.60 centimeters cubed. So each reading builds up an error. However, with a pipette, rather funky looking device, try my best to draw it. Weird body. Yeah, a pipette has one line, and that line fills up to 25. Yeah, if it's a 25 mil pipette. There's no, and then you drain it all the way through. You don't take a final reading. You take one reading when it's full, and then you don't take a second when you drain it, because you drain it all the way to the end. Does that make sense, Ria? Okay, next. Right, which molecule has the shortest distance between the atoms? D. I taught you guys that, fab, no problem. I taught you guys that single bonds, yeah, when you get a CC double bond, it's shorter. Yeah, when you have to have the pi bond, the sideways overlap of p orbitals, this is a head-on, so it's long, but this is a head-on and then a sideways, which pulls them together. Well, this has two. It has 2 pi bonds pulling it together. So in lengthwise, single, double, triple. Yeah. So the shortest distance between the atoms is going to be the nitrogen. I think. Should be. It will be. Next. Oh, we've got to run 2 shapes. Yay. Right. So to run shapes, find your central atom. What group is it in? 4. Add on your attachments. Add 3. Adjust for charge. -1, because it's positive, so it's lost an electron. Yeah, total number is 6. Divided by 2, 3 pairs, that's trigonal planar. So it's got a bond angle of 120, straight off the bat. So it's either C or D again. Wow, lots of C's and D's. The next one is CH3 minus. So this is 4 plus 3 plus 1 gives me 8, 2, 4, but this time it has a lone pair. So it has a bond angle of 107, the same as ammonia. It's actually, yeah, 107. So it's C. That's my answer. Blimey, I feel like there's been a lot of C's. Next. Oh, we saw this. I had to do this twice to make it work. So cyclohexane is non-polar. Nope, hexane, non-polar. Tetrachloromethane. Oh, that's entertaining. Nope. Polar bonds, but non-polar. Trichloromethane, definitely polar. It's D. Next. Which one has the lowest boiling point? The one with the most branches. Every branch you drop anywhere between 2 and 5 degrees. So it's going to be D again. It's got 2 branches. 1 branch, 2 branches. D. Wow. Anyway, state the trend in boiling for the hydrogen halides. Oh, hydrogen fluoride is really high because of hydrogen bonding. Then it drops dramatically when you get to HCl. HCl is DDs. And then it steadily increases again. Right, that's because even though they have DDs, they have increasing London dispersion forces or van der Waals forces. So it goes down and then up, decreases, then increases. So it's a B. Next, which compound is the most soluble in hexane? Well, that there is VDWs or LDFs, whichever one you want to go for. That is H bonding, so that's not soluble. Octane is VDWs. That is soluble. Sodium chloride is ionic. Hells no. And water is HBs. So the one that's most soluble is B, octane. Like dissolves like. Next, which of the reactions is not disproportionation? Right, so bromine starts off with an oxidation state. I'm going to make my pen a bit smaller for this one. Oxidation state of 0. And then it goes to -1. And then it goes to +1. Definitely disproportionation. The bromine has done simultaneous. Yeah, next. So that one is chlorine. Wow, that's interesting. -2. So that must be in a +1. So chlorine's in a +1. Then it's going to this one, which is -6, but to a minus. So that's +5. And then it's gone to -1. It's gone up and it's gone down. That one is disproportionation. Definitely. Next. I should leave those numbers on, actually. They're quite useful to do. It's +1 that for the bromine in that one. And then this one is going to be +1. That one is then +5, and that's -1. Right, fluorine starts at 0, ends at It's still negative, -1. Some students will be asking, how do I know that? The reason being is there's nothing more powerful than fluorine. She's going to notice that she's been written after it. Yeah, this is of 2. Yeah, that means that the F is acting as the negative ion. Because in the naming of anything, you write sodium chloride. The anion comes second in a formula. Yeah, so that one must be the anion. So this is -1. And then this is also -1, not disproportionation, because they've both become -1. So not dis. We'll check the next one anyway. Iodine's going from 0 to +5 in iodate 5, and then -1 there. That one is disproportionation, so the answer is F. Changed my pen back to there. There we go. Next. What is the percentage biomass of carbon in cyclohexane? Oh, okay. So draw out cyclohexane. It's nice to always do so. Yeah, and then stick me. We know that these are all H's. We don't need to draw this all the way out since it's not needed in the marking, but we've got C6H12. So the total MR of that is going to be 12 times 6 plus 12. Yeah, got to be careful. Don't forget, A level is always 1 decimal place. It's always one decimal place. Plus 12, 84.0. Right, and I've also, the percentage of it is 12 times 6 over that number times 100. 12 times 6. 12 times 6 gives me 72 divided by 84 times 100, and I get 85.7%. So it's B. Next. What is the maximum volume of carbon dioxide that could be produced at room temperature and pressure? I hate these questions. Gas ones just boggle my head. So they have given us 0.1 moles of that guy. Right, what's the ratio to CO2? Yeah, we're looking for the maximum volume of CO2. That's all. So the ratio is a 2 to 6, which is the same as a 1 to 3. So if I had 0.1 moles of that, I'm going to have 0.3 moles of that. Agreed? Right, so now I can just multiply it. Oh, hang on. Number of moles is V over 24. Edexcel is so strange, you know. They fluctuate between PV equals nRT and this guy. You can't forget it, but you're going to be using PV equals nRT, or new spec uses that. So number of moles times by 24. So 0.3 times by 24, and I get an answer of 7.2. So it's A. Haven't had an A in a while. Nice to see one. Next, 16. Marble chips react with hydrochloric acid. Fine. The experiment was carried out to measure the initial rate of reaction at 20 degrees. The experiment was repeated, keeping the mass of the marble chips, the volume, the concentration constant. Which set of changes will result in the fastest initial rate of reaction? Right. Size of solid particles are doubled. Size of the particles are doubled? That's going to slow it down. Size of the particles halved? That will increase the rate. Yeah? We're going to make them smaller, half their size. Bigger surface area. So it's either C or D. And an increase by 10 degrees Celsius. So it's D. It's very odd. Seems an odd question, that. Next, methane reacts with steam and an equilibrium is established. Okay, the pressure is then changed and the equilibrium percentage shifts to the right, producing more carbon monoxide. What was the change in pressure and the reason for the change in equilibrium? Right, hang on a sec. The pressure is then changed. So they changed the pressure, but we don't know whether they did it up or down. Yeah, and the equilibrium shifted to the right, left to right. It went that way. Right, on this side, there are 4 moles of gas. Yeah, 1 and 3. On this side of the equilibrium, there are 2 moles of gas. And we shifted towards the 4 side. They've made more gas. We decreased the pressure. Yeah? So it's either A or B. There are more molecules on the right-hand side, and we're done. Thank you. Thank you. Next, which is always true for an electrophile? It accepts a pair of electrons to form a covalent bond. An electrophile, an electron pair acceptor. To make a bond, yes, sure. I'm going to say A is true, but I'm going to check the rest of them as well. It donates a pair of electrons to form a No. Nucleophile, yeah. Electrophile. Nucleophiles are electron pair donors, yeah. Whereas electrophiles, that's an elec, that's a nuke, yeah. So that one's definitely not right. No. It has a negative charge. No, because you've got nucleophiles which are neutral. And positive? No. So A, winner. A greenhouse gas allows Earth to warm up by absorbing energy and slowing the rate at which the energy escapes into space. The efficiency of the greenhouse gas is determined by the ability to absorb infrared radiation and how long it remains in the atmosphere. Maybe. Infrared radiation. Infrared radiation. Oh, right. It is infrared, so it's either A or B. Greenhouse gases are about IR. UV is the ozone, so it's nothing to do with UV. And how easily it forms a free... No. Let's say it's A. I'm not sure on that one. That's interesting. I thought there would have been something to do with it being polar. Oh, which is now. Which type of bond and molecules absorb infrared radiation? Types of bond, polar. Ooh. Polar and polar only. Oh, hang on a minute. The types of bond that absorb it are polar ones. So it's either B, C, or D. And then, but the thing is, you can have polar and non-polar. So it's D. 20 is D. I think that brings me to the end. Right. Right. I need to check my answers. Did I get any wrong, folks? Did I get any wrong? You guys should have done it and marked it already. Did I get any wrong? I'd be surprised if I didn't. Even at AS, they get even harder at A2. At A2, I'm guaranteed there's, and every now and again, I get full marks on this. It's going to take me ages to backtrack all the way through this. Unit 2 mark scheme. Right. If I rip that out and then go and then do that. Right, let's check the marks. How are we doing for time? 25 minutes. That's not bad actually for multiple choice. So 1 is B, 2 is C, 3 is D, 4 is D. Ah! Nope, 4 is A. 4 is A. 5, 6, and 7. 5, C. 6, C. 7, D. 8, C. 9, D. 10, D. 11, B. 12, B. 13, C. 14, B. I'm waiting to get one wrong. 15, A. 16, D. 17, A. 18, A. 19, A. 20, D. Winner. I wasn't sure on the last one. There we go. So, quite happy with that. I hope that makes any sense. If anyone has any questions, please just ask. Right. On to section 2. See how long it takes me to do this. There are 4 structural isomers with the, okay. Butan 1-ol is one of the structural isomers. 2 reactions are shown below. Okay. So reagent B, ooh, look at that. They reacted it with sodium metal. Isn't that nice? Yeah, they reacted with sodium metals. That's Na, that. Yeah, that's the test for all alcohols. Acidified potassium dichromate under reflux. Primary. It's going to become an OIC. Draw the displayed formula of compound A. So the displayed, all bonds must be shown. So that's under reflux, so it's going to become a carboxylic acid, go through oxidation twice. You must show your hydrogens. I had a student once, very sad, who just didn't show any hydrogens and lost so many marks. So sad. Identify reagent B, sodium metal. It says identify, which means you can actually give a formula if you want, but I wouldn't. It's nice to be sodium metal. Next, identify name of formula, the possible reagent for step number 1. Ah, that's interesting. Huh. That's really strange. I mean, it's going to be ammonia. It's got to. Oh, hang on. Whoa. Right. Okay. So you can't just do a straight switch. You've got to convert that first. I need to turn that into a Cl. Identify possible reagent for step number 1. Concentrated HCl. I hope it's going to be interesting to see if they want concentrated. Give the structural. Oh, you could have gone for. No, I prefer conc. I just prefer conc HCl. Give the structural formula of X. Structural. Luckily, they've given you a helping hand by giving you structurals for all the rest. There we go. Identify by name or formula the reagent for step 2. It's ammonia solution. Ammonia. Probably just accept ammonia. Suggest why the reaction in step 2 is carried out by heating in a sealed tube instead of heating under reflux. Ammonia is a gas. NH3 is a gas and would escape. That's why you're doing sealed tube. Would escape and therefore not have a reaction. It'll just escape through it, so you have to seal it. Next, as well as butan 1-ol, there are 3 other structural isomers with molecular formulas of C4H10O. Draw the structural formulas. Okay. As well as there are 3 others, so I can't draw butan 1-ol. Oh, that's mean. Or butan 2-ol. 3 others. Can't do okay. Let's put a branch on it. There we go. Displayed formula. I've got to show all my H's too. Oh, that's going to take me ages, that. There you go. Then we've also got the OH in the middle. There you go. And then stick me. Got to show it in exams. You got to show all the H's. I'm being good. There you go. There's one more. Actually, there's loads more. Oh, that's our alcohols. Oh, blimey. Eek, that's tricky. 6, 7, 8, 9, 10. That are alcohols. You can't put it anywhere else. As well as butan-1-ol, there are 3 other structural isomers that are alcohols. Draw the displayed for each of them. Butan-1-ol and butan-2-ol. Oh, so they haven't given us butan-2. Fine. So they haven't given us butan-2. It's the only other one. There you go. I'm making up the questions. You put it on top of the C in the middle. You can put it on top of the C. No, you can't. Ivan. Is that Ivan? Who's Mean Beans? I always forget. You can't put it on top of the C. That there, if you put it there, that's the same as that one. No, can't do that. Yeah, it's butan-2-ol. I was ad-libbing the question. I was adding in words that weren't there. They just said, as well as butan-1-ol, there's 3 others. You haven't mentioned butan-2. It's Ivan. Oh, shoot. Okay. Just to explain, Ivan, just to explain that to you, look at the picture. Yeah. You looked at it and you saw this. Yeah. I'm just going to show the sticks for a minute. Yeah. So you saw that being different to this, yeah, but in fact what we realize is it actually, oh, hang on a sec, sorry, because that one is actually different. Lol. Really stuffed that up. If you were to name them, Ivan, if you were to name them, that is prop 1-ol 2-methyl, yeah, that's 2-methyl prop an 1-ol. Agreed? Well, look at this one. Oh, prop 1-ol 2-methyl. 2-methyl prop and 1-ol. It's the same thing. Yeah, do watch out for those. Easy mistakes. Easy. Watch it. Alcohol Y has a molecular formula and is not butan-1-ol. The mass spectrum has a major peak at 43. This peak is formed from the fragment of one bond in the alcohol. Draw the list of the species that could give this peak. 43. I've got to get my calculator. 43, and it's not butan-1-ol. Let's go butan-2-ol. Let's cut that one in half. So that's 29, isn't it? That's 29. What's this side add up to? 12 plus 12. 12 plus 12 plus 1, 2, 3, 4, 5. Plus 5 plus 16. 45. That's not the right answer then, is it? Can't be that either. That's interesting. Right, so it's not that one. How about if I just cut that off on one of those guys? Yeah, 12 times 4 plus 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 9. 57. Too many. Cut it there. What's that one add up to? I'm looking for 43. What's this add up to? 12 plus 16. 12 plus 16 plus 3. 31. Not enough. Other one. 12 times 3 plus 1, 2, 3, 4, 5, 6, 7. 43. There it is. There's the section that's causing it. Draw the displayed formula of that guy. Right, so it is 1, 2, 3, and it's off the second. Positive charge goes here. Put everybody else back on. That's hard, folks. Yeah, that's your first really tough question of this paper. God, how many of you got that? I'll be impressed if you did. How many people forgot the charge? Darn it, Is Mr. Duncan frozen or is it just me? Oh no. Oh no. Hide. Have I frozen? It's just you. Ha! Could you also get the same group on the second diagram? Same group on the second diagram. No, you can't. You can't, can you? Because you're looking for 43. You can only cut it once. So you can only cut it here, but that's going to be too big. We know that already. Or we could cut it here, and that's too big, and that's too big. Can't do it with that molecule. Just can't do it. It's a great question, isn't it? Because there's only one person who can do it. Fascinating. Draw the displayed formula of the alcohol Y and label the bond that is broken. So it's got to be 2-methyl propan 1-ol. Has to be that one. It's the only one that you can cut off the bit that you need. Yeah, because what am I cutting off? I'm cutting off the whole section here. Yeah, let's actually do it properly. Displayed, got to show them all. I hate doing them in my exams. I'm just like, it's such a waste of time. And then label the bond that's going to get split. That one. Yeah, you need to lose. Is that the one that Mean Bean spoke about, where you put the OH on the branch? Say that as well. Yes. It's just 2-methyl propan 1-ol, folks. Yeah, they're the same thing, but you have to cut it here. Yeah. Sorry, 2II. Yes, they'll allow it. As long as you show the correct bond being broken. Absolutely, totally fine. Yeah, you can do that. Absolutely, Ria. Yes. If you want to draw Mean Beans and put it on the breakage up that way, you can do. I can draw that for you if you like. Yeah, so you could alternatively do this. Yeah. You could alternatively do that and cut it there. Yes, absolutely. Next. The question is about... Oh, hang on a minute. Yeah, label the bond that is broken. That's fine. This question is about halogens and some of their compounds. Iodine monochloride and iodine trichloride are interhalogen compounds. Draw a dot and cross diagram for iodine monochloride. All right. It's not very hard. It's only 2 atoms. It's easy. If you want it to scale, folks. Sorry, I shouldn't really bother, should I? Yeah, there's the I. There's the Cl. Right. Dot and cross in the gap. Yeah, this is easy. This isn't even complicated. Yeah, and it's a nice and easy one. Suggest how the electrons in the outer shell of iodine rearrange to form iodine trichloride. Wow, they hybridize. Are they actually asking you to do that? They're promoted into higher energy levels. Wow. Suggest how the electrons in the outer shell of iodine rearrange to form iodine. I'm just going to draw it. Just going to draw it. And iodine had 7. 1, 2, 3 so far. 4, 5, 6, 7. Cl. Just do that. There you go. That's fascinating. I don't think this is going to be enough. That sucks. Yeah. So we're going to say that what it hybridizes? I taught this to you, but not expecting them to ask it. They arrange themselves so that there are 10 electrons in the outer shell. Wow. I don't know really what to write there. Suggest how the electrons in the outer shell rearrange to form. Electrons are promoted. I'm going to do it properly. Electrons are... no, hang on a minute. Subshells. I'm going to do it properly. Holy moly. I'm going all the way here, folks. So for iodine, need the periodic table. So for iodine to do this, yeah, what's going to need to happen is these electrons here, which currently look like this, shouldn't do that. Currently look like that. Yeah, in these orbitals. What happens is these get, one of them gets promoted up again to give it more space. Yeah, so you've got, making a mess of this. Ooh, I've just never seen them ask it. Here's iodines before, and it can make, one bond because it has one electron in that last orbital. It can make one. How does it end up making another? How does it make another one? Well, what it does is it steals one of the orbitals above it. Yeah, it steals one of the Ds. Just one, promotes it, hybridizes it, so it forms an S. No, it forms a, a P3D hybrid. Huh, fascinating. That's what it suggests. To give it 4, and what it would look like is this. Can now make 3 bonds. It's bigger. Wowzer. I want to see the mark scheme for that straight away. Holy moly. Mark scheme. Wow. Guys, that's a really hard question. What do they want you to say? Dot and cross. Yeah, fine. First point, one of the 5p electrons is promoted. Wow, from the P to an empty 5D. Wow. Iodine can now form 3 bonds. They did it. Fourth point, expands its octet rule. Wow, guys, be scared. That's hard, that. So they actually wanted you to do it. I didn't think they actually asked any. That's EdXL for you, folks. Yeah. 1 electron promoted. It's only 2 marks. Don't panic. 1 electron promoted from 5p to 5d. Can now make 3 bonds. 3 bonds because of 3 half-filled orbitals. Can hold outer electron, hold tons of outer shell, outer energy level. Can hold 10. Wow, that's mental. And the diagram really wouldn't have helped you. I'm absolutely staggered, folks. Wowzer. Sorry about that. It's hard. EdXL and their infinite wisdom. The iodine trichloride molecule is T-shaped. State whether the ICLs are polar and whether ICL is a polar molecule. The answer is both are a yes. Yeah, so because chlorine is like 3.5 and iodine is like 2. Yeah, so ICL bonds are polar. They are polar due to Cl having a higher electronegativity. Electronegativity. Very easy to get that wrong. Negativity. Second mark. Molecule is not symmetrical. It's not symmetrical. So is polar. Do want to check that as well, though. How fascinating. 2 really great questions. Cl bonds are polar because chlorine is more electronegative than iodine. There you go. Is polar due to it not being symmetrical. Winner. Thank you. Move on. Give the color. Oh, thiosulfate. Oh, no. Oh no. Blimey. Thallium exists in more than one oxidation state. Thallium ion, yada, yada, yada. In an experiment, thallium 3 plus was added to potassium iodide solution. The iodide produced was titrated with sodium thiosulfate. The titration was repeated, and the mean titer was this. The titration was carried out without an indicator. Interesting. The indicator is usually starch, by the way, because of the iodine. Yeah. So give the color of the endpoint. Right, guys, you're reacting the iodine that's being produced, yeah, which turns it brown. So it's going from brown to colorless. Yeah. It's not really brown. It's like an orange, because iodine's not particular. I'm going to go brown to colorless. Need to check the mark scheme. Shocking how many times I'm checking the mark scheme on this. Yeah. Yellow. Ignore clear. Any other color with yellow? Pale yellow to colorless. Oh, I knew they were going to do that. Iodine's not very soluble. And by the way, flagging that up, I got it wrong. Yeah, iodine in thiosulfate titrations is yellow to colorless. But usually, by the way, it's actually a pale yellow. That's actually kind of important. That's why you need an indicator. And what you do is right near the endpoint, you add starch. You can't add the starch early because you'll get what's called flocking. It clumps together and it doesn't work then. Calculate the ratio of moles of iodide to thallium and hence deduce the final oxidation number. Wow, that's really hard. Okay. Thallium exists in more than one oxidation number. In an experiment, right, so they took thallium 3 plus, was added to excess potassium iodide, right, and the thallium in an experiment, this was 25 centimeters cubed of 0.0464 moles per dm cubed. Right, so straight away, let's just run moles. I think that's reasonable. C, 0.0464, times by V all over 1,000. All over 1,000, because I'm in centimeters cubed. So thallium's 3 plus, I have 1.16 times 10 to the minus 3 moles of it. It's probably going to mark somewhere. Next, was then added to excess potassium iodide. Okay. The iodine produced was then titrated with, right, okay. With excess potassium iodide. The iodine produced. Oh, okay. So the thallium 3 plus oxidizes iodide ions to iodine. Right. And then what we want to know is we want to know what thallium has become. But we need the ratio of these guys. Well, we can certainly figure out the ratio of that one to that one, can't we? Because we've got the moles of thallium 3 plus, and we can work out the moles of iodine from the titration. Right. So we now need to work out moles of thiosulfate, which is this guy. Yeah. And there it is. So for thiosulfate, S2O32 minus, yeah, we've got 23.2 centimeters cubed. So how do we know when to say yellow-brown when it comes to iodine solution? I know, Kayun, it's such a nightmare. Right, Kayun, the only way you ever see brown for iodine is when there's potassium iodide in with it. This potassium iodide increases the solubility of iodine because it adds another charged ion in there, which helps dissociate the crystal. I know. I don't even know how to answer that, Kayan. The answer is most of the time you're saying yellow, but then if you ever do it in, and then you're going to form a black solid. It depends on the question. There are subtle hints in the question. I apologize for that one. It's not easy. The concentration was 0.1 molar. I'm switching to molar. You're not allowed to use it. C, 0.1 times by V, 23.2, all over 1,000. So I've got 2.32 times 10 to the minus 3. Right. So that there is the number of moles of thiosulfate. What's the ratio to iodine? It's a 2 to 1. Ratio is 2 to 1. So divide that number by 2. Divide by 2, still on my calculator. So I get 1.16 times 10 to the minus 3 moles of iodine. Ah, right. Well, guys, right. So we've now got 1.16 times 10 to the minus 3 moles of iodine. Yeah, that's I2. Right. Well, the ratio of those is always going to be 2 to 1, isn't it? You've got to have 2 of those to make 1 of those. Everyone agree with that? Yeah. So how much iodide then reacted? Is that what I need to do? What's the iodide that then reacted? Times it by 2 again. So 2.32 times 10 to the minus 3 moles of iodide reacted with thallium. Right. And it told you the amount of thallium. So look at the numbers. Look at the numbers. Here's the thallium number. Here's the thallium number. Here's the iodide number. What's the ratio? It's a 1 to 2, isn't it? So one of those reacted with 2 of those in the molar ratio. Divide them all by the smallest. Right. What does that now tell us? It tells us that we required 2 iodides, and that formed the iodine, and it will spit out 2 electrons. Yes, that's going to spit out 2 electrons, folks. Well, hang on a minute. That's also going to react with the thallium, and the thallium is going to accept those 2 electrons. So it's going to become thallium 1+, because it has to accept +1. It's going to become thallium 1+ because the thallium has to take that one thallium 3+ must accept the 2 electrons to become thallium 1+, because the electrons have to cancel. Holy moly, that's hard. I want to see how many marks you'll gain without having to work out the final charge of that. That's just fascinating. Wowzer. You ready? Ooh, blimey. There you go. Blimey. So where do we get our marks from? This is an interesting marker, this one, folks. I'm just going to... I'm trying to split my screen so I can see both. Right. So first thing I wanted to do is work out the moles. I got the mark for the moles there, which is that one. And then I worked out the moles of the other guy. Moles of the thio. I got that mark too. There's that one. Yeah. This third mark shows that the ratio is a 2 to 1. I got that mark because the ratio of the moles, you just looked at the moles and you worked out the ratio. And then you got 1 mark for the oxidation state being +1 at the end. Guys, that's hard. That's hard, folks. This is the level they're expecting you to work at. I need you guys to be on this. And I know the fact that I don't know how many people are still watching, but I think I'm wondering now, we've come up to an hour. We're up to question 23. How many questions left? Right, I'm going to end the webinar now. We've done an hour. I'm going to end it early, and I'll do part 2 tomorrow. End of part 1. You right?
Yeah.
Just throw it on the floor.
Just like today. Not paying attention.
Is that what it is it? There we go. Right, guys. I'm going to leave you be now till tomorrow. That last question was hard, folks. And it takes practice. Yeah, it really, really does. Do make sure you're doing these papers. When we get back to school, folks, you're going to have a paper to be doing for homework all the time. Yeah, I need you guys to be on this. This is tough. And this lays great foundations for next year. Yeah, for year 13. Guys, thanks for coming. Is part 2 same time tomorrow? Yes, I'll do part 2 tomorrow, Ivan. Yeah, I'm really excited for tomorrow. Oh, I still can't tell if you're being sarcastic, Ria. Guys, have a great rest of your day. See you soon.